Right, so this is the first of my two sessions on how do we do proofs. And there's no way I could teach you how to do proofs in two sessions. So all I could do is address just a few of the issues and recommend to you that everything you see in the Pure Maths modules this semester will be helping you to see how to do proofs. Also, there's all the question sheet questions. And again, there's nothing better for learning how to do proofs than doing proofs. That's really what you've got to do. But I'm going to try to address some of the issues that appear to give some people sort of mental blocks against proof. People who don't know where to start. Maybe I could indicate some of the things that will ensure that people do know where to start, or at least give you a good chance. So last year, you would have seen lots of different proofs and lots of different kinds of proof. And as an exercise, you can make a list of all the different kinds of proofs that you can think of and see if you compare with your friends and see if you've come up with every different kind of proof that you think you've seen so far. In these two sessions, I'm going to be focusing on what we call direct proofs. So this won't be proofs by contradiction. This will be the kind of proof where you're given some information and asked to deduce something else from that information. And you're asked, you can do it if you know the definitions and you've got some ideas of what steps to try next. You can do a direct argument with logical steps and arrive at the conclusion that you want. Which is basically what it says here. Now, you may be using standard definitions. You may be using some facts that you've previously proven. You may be using logical reasoning. You may have to have some ideas in the middle of the proof in order to decide what to do next. Or it may be a proof that sort of writes itself. And I'm going to try to convince you that at least some elements of doing proofs are relatively systematic. I'm not claiming that you can automatically construct proofs without having ideas. I'm not saying there's no creative element to doing proofs. What I'm saying is that there are some systematic elements involved in doing proofs which you should know about so that you don't get distracted from having your ideas by having to try and think about stuff that should be relatively routine. So do as much as you can on the question sheets, because they're full of proofs, and there's nothing better for learning how to do proofs than trying to do proofs. So as I said, you may need to come up with some clever ideas. Probably not very many clever ideas needed in the second year pure modules. Most of the proofs are relatively systematic and direct without needing too many interesting ideas. The number of interesting ideas you need in the proofs, certainly in mathematical analysis, there's a very small number of ideas that you might have found difficult to think of for yourself. Most of the rest is fairly systematic. But when you do have to come up with ideas, it will help if you're not having to think about the systematic elements of doing the proof. If those bits come automatically, then you'll have more resources available to try and think of the ideas that you need. So here's a question about odd numbers. And there are lots of different ways to do it. And I'm going to let you have a go at doing it. But I'm going to suggest some hints that might help you to do it, to give you one way of doing it. I'm not saying that's the best way of doing it. It's certainly not the only way of doing it. But it's just a couple of hints that would indicate one particular way of doing it. So here's the question. You have to prove that for every odd integer n to the fourth minus 1 is divisible by 8. Now, as it turns out, in fact, it has to be divisible by 16, which is better. But I'm not asking you to prove that. That's an additional challenge. If you succeed in proving it's divisible by 8, then you can have a further think and see whether you can prove that it's divisible by 16. Here are some hints. There's no way to answer this question if you don't know what an odd number is, and if you don't know what being divisible by 8 means. So you should make sure you know those definitions. It's almost impossible to prove anything properly if you don't know what the definitions are. And then, because you're asked to prove something for every odd integer, a typical thing to do, if you're asked to prove something is true for every odd integer, you should start with the statement, let n be an odd integer. You've then made the assumption that n's an odd integer, and if from that you can deduce the result you're supposed to get, then since you only assumed that n was an odd integer, it must be true for all odd integers n, because you're not going to be assuming anything else about n. So if from the oddness of n you can deduce that n to the fourth minus 1 is divisible by 8, then you've finished. And finally, for one of the many possible proofs, you might find it useful to use a binomial expansion, which tells you what the fourth power of a plus b is. Now, I did find in the past that second years have forgotten the binomial expansion, even when it came to second year exams, occasionally. In fact, I've seen second years attempting to multiply out brackets and getting it wrong, and coming up with an incorrect formula for, say, the cube of a plus b. So that's happened in the past. I suggest it's a good idea to know the binomial formula for expanding a plus b to a power. So if you don't know it, I suggest you think about it. Now, let me pause the recording there, and we'll come round and see how you're getting on. But feel free to talk to each other and talk amongst yourselves and have a go at this question. So you've had a good go at this, and quite a few of you have managed to prove that n to the fourth minus 1 has to be divisible by 8 when n is odd. And I've challenged a few of you to try and push that a bit further and get it that it's divisible by 16. There are lots of different proofs of this. You can use modular arithmetic. It's probably the most efficient proof, if you remember modular arithmetic from first year, but that's not the proof I've been hinting at here. So I'm going to show you the proof that most of you have already written down, which is a very, very direct proof, directly from definitions and using the hints given. So we've got question 1. Prove that for every odd integer n, n to the fourth minus 1 is divisible by 8. Now I'm assuming that you've reminded yourself of the definitions of odd and divisible by 8, and that you've reminded yourself of the binomial formula for a fourth power, because I'm going to use all of those in this proof. And as I said, you start the proof with let n be an odd integer. That means n is equal to 2m plus 1 for some other integer m. With or without brackets. So n to the fourth minus 1 we can do using the binomial formula. So n to the fourth minus 1 is 2m plus 1 all to the fourth minus 1, which is equal to 2m to the fourth plus 4 times 2m cubed plus 6 times 2m all squared plus 4 times 2m plus 1. That's 2m plus 1 to the fourth power. Put that in brackets and subtract 1 off at the end. And if that simplifies out to 16m to the fourth plus 32m cubed plus 24m squared plus 8m plus 1 minus 1 cancels, which you can write as 8 times 2m to the fourth plus 4m cubed plus 3m squared plus m. It's 8 times an integer, so it's divisible by 8. And we finished. So what did we do? We used, well, let's try and make that full screen. We used what it meant for n to be an odd integer. We said n is 2m plus 1 for some integer n. That gave us something to work on when we were looking at n to the fourth minus 1, because now we had n in another form, and we were able to work out what n to the fourth minus 1 was. And we were pretty sure that we were going to figure out whether the result was true or false when we did this, because this is an exact formula for n to the fourth minus 1. And if you get to the end there and it doesn't appear to be divisible by 8, then it may well be that you forgot to subtract the 1 off at the end, which is easily done. But this was use the definition of odd, use the binomial formula, and essentially, at the end, use the definition of divisible by 8 implicitly in saying that's a multiple of 8, so it's divisible by 8. Now, there's lots of other proofs, and if you've come up with a different proof and you're not sure if it's right, feel free to, you can ask me about it another time. But let's not worry about all the other different ways of doing it this time. This is the typical kind of proof that I want to talk about in these sessions. Use the definitions, use some standard facts, think about what could you try next. There's usually not very many things you can try next. And, of course, that all-important first line of the proof, let n be an odd integer, which is where we make all our deductions from. What do we say? We assume that n is an odd integer, we make deductions from that, we get the result. If it works, then we've proved something is true for all odd integers. Any questions about that proof? Okay. Well, if you do have any questions, remember you're welcome to contact me at any time. So let's go back to the presentation. So I come across a lot of students who say that they think that proofs are hard. We don't know where to start proofs. We think that we're bad at doing proofs. And often it's simply that they haven't incorporated some of the systematic routine elements that you can train yourself in before you even have to start having interesting ideas. Here are some things that I've heard or I thought about. Can you follow the individual steps in a lecturer's proof? I think most people can follow individual steps, but it somehow doesn't help. People have more trouble having the overview of the proof, seeing where are you trying to get to, why are we doing all this stuff in the middle, why would we be trying that? Of course, a lot of proofs are discovered backwards and then written down forwards, because people know where they're trying to get to. They think, well, if only we knew that, that would do it. And if we wanted to know that, all we would need to know is this. If only we knew that, then we'd be done. And then that would be true if I knew this. But then, of course, you've got to write it down all forwards, and that somehow can disguise the fact that the proof was discovered backwards. But if you've got some idea of where you're trying to get to, that makes it a little bit less mysterious why some of these steps get done in the middle of a proof. Once you see the whole proof, do you understand it? Well, line by line, you can probably follow it. And then, okay, you agree it's a proof, but you may still be not happy about where the proof came from and why it works. What about when you want to do the proofs for yourself? Is it enough to just read and understand lecturers' proofs? Or do you find you can do that, but somehow that doesn't seem to help you to find proofs yourself? I think it does help a bit if you read and understand lecturers' proofs. That shows you the sort of language, the sort of structure that proofs have. But there's nothing like doing proofs yourself for learning how to do proofs. So you've just got to keep trying to do proofs yourself. Where did that step come from? Was it magical? Is it mysterious? Why did the lecturer do what they did next? I'm going to try to convince you that quite a lot of things you do are relatively routine, almost automatic. A lot of the proofs in this module write themselves because there's so few options for what you could try next. You've got to use all the information that you've been given. Otherwise, there's something strange about what you're being asked to prove. So you've got to try and use all the information you've got. If you get to the end of the proof and you haven't used some of the information, that's a bit suspicious, because it suggests that you've proved something that's too good to be true. If there's some part of the information you started with that you haven't used, then it's a bit worrying usually. It means that you've probably done something wrong. So is it easier to follow the proofs that the lecturer gives, or is it harder to find your own proofs than to follow the proofs given by the lecturer? I think that's a definite yes. And a lot of people have trouble with the first line of a proof. And this is something, again, that I'm going to be addressing in these sessions. How should you start a typical proof? And a lot of them are going to start the same way, with the word let. You want to make the assumptions that you're given in the statement and try to deduce things from that. So you're almost always going to start with the word let in these proofs. So this is what we proved above, but maybe that isn't the only way to express that statement. Perhaps if we'd expressed it a different way, it would have made it easier to see how to start. So we could have said, let n be an odd integer, then n to the fourth minus 1 is divisible by 8. Now, that actually means exactly the same thing as the other one. They both incorporate the idea that if you know that n is an odd positive integer, then n to the fourth minus 1 is divisible by 8. Which you can say this way as well. The let n be an odd integer is a nice friendly one, because it gives you the first line of the proof already. Because you already have that n as an odd integer, and you don't have to think of the first line of the proof yourself. It's already been given to you. If you're not given it, you have to write it yourself. So if you see it in the first form, you start with let n be an odd integer, and you work from there. The main thing is you're allowed to assume that n is odd, and then you use whatever facts or definitions that you know and can help you to make some deductions until you get to the result you want. And there's going to be an awful lot of results of the form, every object of type X has got property Y. There's going to be loads of proofs of that sort of statement in this module and in other pure math modules. And whenever you see that, the first line of the proof is almost always let x be an object, well, okay, let something be an object of type x. Then you make the deductions and you prove that it's got property y. So if you go back and look at the proof we had before, it's worth revisiting it and checking the structure. Why did we start it the way we did? I've already told you about that. Which definitions did we need to use, and when did we use them? We must have used all the definitions at some point, somewhere in the proof, even if it was just implicitly. Which standard results did we use? When did we use them? And for every proof of this module, you'll get something similar to this. You can look at the structure and see what was used, what were the definitions, when were those definitions used, was all the information used, is this a genuine proof or is there a trick somewhere? And finally, what else could you try at a particular stage? Sure, there's not usually very many things you can try. All you can do at any particular stage is use a definition, a standard result, a bit more of the information that you've already been given that you haven't used yet, or some interesting idea because it's actually a more interesting proof than your typical direct proof, if that happens. And along with that you get, is it obvious why we did each step when we did it? But quite often it's a very natural next step because you've just got to a stage where you can easily use the next bit of information that you haven't used yet. So here's another question about functions from R to R, real valued functions defined on R. It's not a very hard question, and you may have seen these results before, but you can't do it unless you know the definitions of the terms involved. So yet again, you need to make sure you can remember what these terms mean. So here's the question. You have to prove that for every odd function f, that f of 0 must be 0. And then you've got a pair of odd functions, and you multiply them, that you must get an even function. And the third one, if you've got a pair of odd functions, and you compose them, and do f composed with g, then you have to prove you get an odd function again. And you're looking for direct proofs again, just using the definitions. Oh, and here's something I forgot to mention earlier. A lot of the proofs we're going to be looking at are what I call, somewhat humorously, proof by definition. The proof by definition, that's not an official term, is where if you write the definitions of the terms down, you've almost finished the proof. In fact, sometimes with proofs by definition, you write the definitions down and you find you have finished the proof, in which case it's sometimes a bit worrying because you're not sure if you proved anything. But it often is almost as simple as, if you write the definition down, then you finish the proof. Sometimes you have to do a few logical steps in between. In this one, you may have to do a few very minor calculations once you've written the definitions down. So, which terms are mentioned in the question? Do you know the definitions? Could you write those definitions down carefully? And can you reformulate these statements to make it more obvious how to start the proofs? So let's give you a bit of time to think about those, and I'll pause the recording, and again, we'll come around and see how you're getting on. So here were the definitions. As I said, a function from R to R is an odd function. That means that for all x in R, we've got f of minus x equals minus f of x. Whereas if you've got f of minus x equals f of x instead, then that means you're an even function. So for part 1, you're given, so in question 2, part 1, given f is an odd function from R to R, we'll substitute in x equals 0 into this equation here. Try that again. Into the equation f of minus x equals minus f of x, we're going to substitute in x equals 0. So let me call that equation star. we'll put x equals 0 in star, and you get f of minus 0 equals minus f of 0. But minus 0 is 0, so f of 0 equals minus f of 0, which, well, there aren't very many real numbers which are equal to minus themselves, but if you want to throw in an extra step, you can add f of 0 to both sides to get 2f of 0 equals 0. Giving f of 0 equals 0 as well. And I'll just sketch the other two. F of g are odd, then the function fg evaluated at minus x, that's equal to f of minus x times g of minus x. And since they're odd, that's minus f of x times minus g of x, but the minus signs multiply to give you 1, so that's equal to f of x g of x, which is the function fg evaluated x. So fg is an even function. And finally, part 3, we're interested in f of g of minus x. So again, f and g are odd. F composed with g of minus x, that means f of g of minus x. That's the definition of f composed with g. G of minus x is minus g of x because g is odd. That's because g is odd. Had to use that somewhere. Now that's f of minus something, which is minus f of something. And that's because f is odd. But that's minus f composed with g of x. So that shows that f composed with g is an odd function. Again, that's a sketch. You should fill in the missing expression. And we better stop there.